for the quiz. Some of this will overlap with part one, just to make sure we understand it, and then we'll add some new stuff as well. So let's jump in. Again, we're going to learn from this. Light will tell us, we already said what elements make up things like stars, and also which directions they are moving at what speed. So this combines everything we mentioned last time. A spectrum is the amount of light given off by an object in the range of the different wavelengths. So remember our emission lines versus our continuum versus our absorption lines. So our continuum is all the colors. Our absorption lines are those like black empty spots, and our emission lines are the different lines of color there. Go ahead and pause while you try to answer that. All right, unless it's a black hole, we're always going to be able to detect some sort of light. So some of the reflected, and also we're going to be able to see some emitted. Remember, electrons have different energy levels. The least amount of energy level is that first electron energy level, this first shell around the electrons, and the further we get away from the nucleus, the more energy each level has. Remember, this will be a question on the test possibly. Ground state is the lowest energy level, and every level past that are called excited states because you have to have more energy to reach them. Get excited, in essence. If you add the right amount of energy to an atom, the electron can go up energy levels or down. Remember, when it goes down, like we see in this picture, it's dropping down, we give off light. When it goes up in energy level, it absorbs light. And it can get energy from light hitting it as well. You don't need to know Kirchhoff's laws by name, but it says light of all wavelengths shine on an atom. Well, okay, makes sense. And only light of an energy equal to the difference between the floors is absorbed. And that's what causes them to jump up in floors. Notice absorbed is still going up. The rest of the light passes on to our detector. So if we look at this picture, here's the light coming. It's going through cold gas, through this slit, through the prism. And we see what this is the absorption spectrum. Notice the black spaces. Light at all wavelengths minus the specific ones absorbed. That's why they look black there. These are dark hydrogen absorption lines. So the continuous spectrum is in the back, all the colors, and then the colors that were absorbed by hydrogen appear to be black because they don't go through. When electrons get excited to jump up a level, remember, light is absorbed, energy absorbed. They don't stay excited forever. Eventually, they drop back down, and when they do, that's when light is given off in all direction, and that's what we call the emission spectrum, what's given off or emitted. A little bit of a review from last time. Remember, why do we get continuous absorption or emission line? It depends on the energy source, if it's hot and dense, cold and dense, or hot and not dense. Emission lines are unique for every element. Top one's hydrogen, you can see the rest, but they definitely are easy to tell that they're different because they have different numbers of electrons in excited and ground states as well. So scientists, what they need to do is figure out which line relates to which elements. So when they look at something like this, they can say, okay, this star that we emitted this spectrum has hydrogen, oxygen, hydrogen, and nitrogen. Notice that the temperatures of the star are going to affect the colors that are absorbed, which makes sense. As we know, hotter temperatures like white and blue, colder temperature stars are going to be the reds, yellows, and oranges kind of in between. So each element is unique with those special set of spectral lines. It's kind of like their fingerprint. Once you are able to observe them, you know what elements are in it, and you're able to identify the absorption spectrum, emission spectrum, and where that element is. Let's skip this question, won't be on the test. Because the sun is a cool and relatively cool. It's average type temperature. And lower density, this is the kind of spectrum you would see. You definitely see helium. We know it's there because of its spectral lines are present. Remember, this was on our last set of notes, so just a quick review. Redshift means if something is moving away, in this instance, the observer would be where my star is, and the object would be moving away from him, so the wavelengths get stretched out and appears red. If something was moving toward him, they get compressed, the wavelengths, and it would appear blue. That's what Doppler shift was. And the faster they're moving, the bigger the shift. That's a fancy way of saying this. You can look at the pictures if you want, but really it's just saying they'll get pushed closer together. It'll be more towards the blue end if it's coming towards you, and if it's fastly, and if it's going fast away from you, it'll get more towards the red end. The first two pictures show a smaller redshift and a bigger redshift, and then a really big redshift at the bottom. So this object is moving away the slowest, and this is the fastest. And how can I tell that? Well, look, it shifts a little bit here and a lot down there toward the red end. And you don't have to use the red. If we look this line, it's shifting toward the red end of it, and it's shifting even more toward the red end at the bottom. So it doesn't have to just look at the red end. It's moving towards that end. That's why they call it red shift. Whoa, what's going on here? And that should do it. Again, I think the practice questions are every bit as important, and I would definitely take notes, especially on the ones you missed, to get ready for this extra credit quiz.